Okay, so good morning once again. We're going to go to the fifth lecture in this series. Remember from the last class, I promised that I was going to share the slide of the examples. On our last slide, the solutions were not portrayed on the example. Yes, we only solved them in class. We tried to solve it together via the chat page. So today, this is one of the examples, and this is the example under Route's law, where you have, I hope you cannot hear me. Please type yes in the chat box if you can hear me. Oh, fantastic, good, thank you. Okay, so the first example was 80 grams of C12H22O11 was dissolved in 100 ml of water. So we have 80 grams of sugar dissolved in 100 ml of water. What is the expected vapor pressure of this solution at 25 degrees centigrade? Now, assuming that the vapor pressure of water at 25 degrees centigrade is 0.0317 torr. So because this is a non-volatile solute in solvent, we are going to use the second formula, which is P, the vapor pressure of the solution, is equal to the mole ratio of the solvent multiplied by the vapor pressure of the pure solvent. Now, for us to do this, what we have been asked to calculate from the question is this P. Now, for us to do this, we need to get the mole ratio. Remember, your mole ratio is the mole ratio of the solvent, in this case now, is the number of moles of solvent divided by the total number of moles. The total number of moles is the number of moles of the solute and the number of moles of the solvent. So here, we know that a number of moles is equal to mass divided by molar mass. So in order for us to get this mole ratio, we need the total number of moles of both the solute and the solvent, which means we need to work out the number of moles of the solute, the number of moles of the solvent, and then add the two together. So here, in order for us to calculate the number of moles of the solute, we needed to calculate the molar mass of sugar. Now, I took the pain to solve this out because I think somebody in the chat box was asking, how can I calculate the molar mass of sugar? Even though that question is it's quite ridiculous at this level, I'm sorry to say, but we are in the class. So I've taken my time to work this out. Subsequently, you may not be so lucky for us to calculate molar mass during any kind of question that involves the calculation of molar mass. Okay, so the molar mass of sugar is equal to 12, which is this subscript here. So it means that we have 12 moles of carbon in this compound. We have 22 moles of hydrogen, and we have 11 moles of oxygen. So in order for us to calculate the molar mass, we need to multiply this, the atomic mass of each of the constituents. Now, the constituents of this sugar is carbon, hydrogen, and oxygen. So we need to multiply each of the constituents with their number of moles. We need to multiply the atomic mass of each of the constituents with their number of moles. So the atomic mass of carbon is 12. That's why you have 12 times 12, which is the number of moles. We have 22 moles of hydrogen, and the atomic mass of hydrogen is 1. So this is 22 times 1. We have 11 moles of oxygen, and the atomic mass of oxygen is 16. So we have 11 times 16. When you take the total of this, you're going to get 342 grams. Now, like I always tell you in FSC 112 class, don't always depend on this constant when you are not given in the exam hall. There are some elements that we expect you to know the atomic mass by heart because you have solved calculations involving them several times. So elements like carbon, hydrogen, oxygen, they are very common that you shouldn't be waiting for the atomic mass to be quoted. I think that was what confused the, what's his name now? Is this Simi now? I can't remember the name. So maybe because we didn't say carbon is equal to 12, hydrogen is equal to 1, oxygen is equal to 16. So you were quite confused on what to do. So please, some of these elements, some of these atoms, please, you don't, sometimes it might be given, sometimes it might not be given, but there are some basic ones that we know that you should know by practice because we use it all the time. All right, so that said, we now go ahead to find the number of moles of the solute. Now, the number of moles is mass over molar mass as quoted here. The mass was given in the question, 80 grams of sugar was dissolved in 100 ml of water. So you have 80 grams divided by the molar mass, which is 342. If you work out this mathematics, what you're going to get is 0.234. That's sorted. We then move on to the solvent, which is water. The number of moles of water again is mass divided by the molar mass. How did we get 100 grams as the mass of water? Remember that your water is liquid, so we have it in volume. In order for you to get the mass of water, we need to use the formula density is equal to mass divided by volume. In the case of water, the density of water is 1.0 gram per mil or 1.0 gram per cm cube. So it is 1. When you multiply 100 mil by 1, what you would have is 100 grams. So that's why the mass of water is 100 grams. So mass divided by the molar mass of water. Okay, you can see from here that I didn't have to calculate the molar mass because we've done this extensively here. But how did we get 18 here? The atomic mass of hydrogen is 1, and you have water as H2O. So it means the number of moles of hydrogen is 2. So 2 times 1 plus 16, which is the atomic mass of oxygen. So 16 plus 2 is equal to 18. So that's how we got the molar mass of water here. And we divided the mass by the molar mass of water to get 5.5 moles. Remember that your total number of moles is the number of moles of the solute plus the number of moles of the solvent. So here, this is the number of moles of solute, and this is the number of moles of solvent. And we said for you to get the mole ratio of the solvent, it's going to be number of moles of solvent divided by the total number of moles. Now, the number of moles of solvent from our calculation here, water is the solvent, is 5.55 moles. So we have 5.55 mole divided, okay, there's supposed to be mole here, do not forget, it's an omission. So 5.55 plus 0.234 mole. This is 5.55, this is 5.55 divided by 5.784 mole. And the answer for that is 0.960. So we have the mole ratio of the solvent to be 0.960. Now we can slot in this value into this equation that we have here. And when we did that, now have P, which is the vapor pressure of the solution, equal to 0.960, which is the mole ratio of the solvent, multiplied by 0.0317, which is the pressure of the water, that's the pure solvent. So what we have is 0.030. So for those of you who couldn't get it in the last class, I hope this is much clearer. So if you're one of those who was confused from the last class, you can just type better, I understand now, something like that, so that I can know you're following. So if you're one of those who was confused from the last class, please just type better. So I'm talking to just those people who didn't understand. Okay, thank you, Riyomi. Okay. All right, so, oh, thank you, Oluwatomishi. Can see your chat. Now, the second question, the second example, this is on boiling point elevation. When we started talking about the effect of this mixture on the boiling point of the solution. So the example is a solution prepared from 1.25 gram of oil of wintergreen and 99 gram of benzene has a boiling point of 80.31 degrees Celsius. Determine the molar mass of the compound. Now, benzene's normal boiling point is 80.10, and the constant, that's the boiling point elevation constant, is plus 2.53 degrees Celsius per molar. So we know the equation for calculating the boiling point elevation. So this is change in temperature of the boiling point is equal to the boiling point elevation constant multiplied by the molality of the solute, the molality of the solute. From this equation, from this question, you can see you are asked to determine the molar mass. So you are given the change in temperature. You are given the change in temperature because you have an initial boiling point and an elevated boiling point. So from these two values, you can calculate your change in temperature. And you're given the constants, the boiling point elevation constant, which is 2.53 degrees Celsius divided by molar. So just in case you don't know where the molar mass is coming from, out of three variables, you already have two knowns. So you already have two of them known. So the first thing to do is to look for this one that is not given. So we made hem, which is the molality of the solute, the subject of formula. When you do this, this will be equal to change in temperature divided by the constant. So we have the change in temperature here, 80.31 minus 80.10, divided by the 2.53, which is the constant, the boiling point elevation constant. The answer we get from there is 0.083 molar. Notice that this M is small letter. That is the M for molality. That's the M for molality. If you're talking of molarity, that is capital letter M. So please be very conscious of these concepts. A lot of you calculate your molarity in your lab. That's your titration. And you write molarity as small letter M. It means a very different thing in chemistry. So please always be conscious of some of these conventions. Okay, so now that we have the molality of the solute, we now want to work out the molar mass of the solute. Remember, a solution prepared from 1.25 gram of oil of wintergreen in 99 gram of benzene. So that tells you that benzene is the solvent and your wintergreen is the solute. Now we want to calculate the molar mass of wintergreen. We know that the molality is equal to number of moles of solute divided by mass of solvent in kilogram. This is very, very important. This is where a lot of people make mistakes. They forget to convert the mass of solvent to kilogram. So always take note of this. Molality is equal to number of moles of solute divided by mass of solvent in kilogram. Quickly, type in the formula for molarity. Now, this is molality. I want you to type in the formula for molarity in the chat box quickly. I have just 2 minutes to do that. Anyone? Mass concentration over molar mass. No, Damilola, that's not correct. Mass concentration. Damilola, think, okay, mass concentration divided by molar mass. Oh, yes. No, I am, okay, that's nice. Okay, so I'm talking in terms of the number of moles. In terms of number of moles. Thank you, Damilola, you're actually correct. Okay, fine. All right, so number of moles divided by volume. Thank you, N over V. Thank you, Okunlaya. Thank you, Mike. Okay, so you still remember that. So you can see that the difference between your molality and your molarity is that you are dividing the number of moles of solute by the mass of solvent in kilogram for molality. While in molarity, you're dividing the number of moles of solute divided by the divided by the volume of the solution in dm cube. Thank you very much. All right, so let's get back to the example. So we have a molality equal to number of moles of solute divided by mass of solvent in kilogram. So a number of moles of solute, so we want to make the number of moles the subject of formula, because now we have molality from the previous step, and we have been told that this solute was dissolved in 99 grams of benzene. So now we made number of moles the subject of formula, multiplied by 0.083 mole per kg. Now, oh, this is per kg, sorry. This is per kg, please, per kilogram. Now, for us to find it easy with our units, I've decided to write this out, this molality out in its SI units, so which is mole per kg. Please take note of this. I think it will be corrected on your notes before it's uploaded if it's like that, but please just take note, it's mole per kg. So there's supposed to be -1 here, or you change these dots to division. Now, which is 0.083 times 99 times 10 raised to power -3. So this is the conversion factor from gram to kilogram, from gram to kilogram. Now, when we work that out, a number of moles is equal to 0.00822 mole. Once you get your number of moles, it's easy for you to get your molar mass. Remember that general formula, that very popular formula, mass is equal to number of moles divided by molar mass. If you made molar mass the subject of formula, it becomes molar mass is equal to mass divided by number of moles. When you do that, your answer would be 152 grams per mole. And it's easy for you to check if this solution is correct, because wintergreen is methyl salicylate. So if you just pick your phone, Google molar mass of methyl salicylate, what you're going to get will be 152 grams per mole. So I'm sure with this discussion, those of you that couldn't grasp this in class on Monday, you are much better now. Please take time to solve the practice questions. All right, so we move to today's class. Yes, the very interesting chemical thermodynamics. Chemical thermodynamics. In chemistry, chemical thermodynamics is very important, and it has a whole lot of relevance. So when you talk of physical significance, chemical thermodynamics is at the heart of almost every industrial activities and even some natural phenomenon that we experience from day to day. Some of these will be discussed as the class goes on. So we're talking about introduction to chemical thermodynamics, usefulness of thermodynamics, and some mathematical symbols. Now, this class, we're just going to focus on definition of some terms. So chemical thermodynamics, what is chemical thermodynamics? I hope this is not interfering with your vision. Okay, so chemical thermodynamics is the study of how heat and work relate to each other, both in changes of state and in chemical reactions. Chemical thermodynamics is the study of how heat and work relate to each other, both in changes of state and in chemical reactions. So you see, everything in life, everything in this world is chemistry. Like our popular slogan in the chemical society is, what in this world is not chemistry? So everywhere you are, a couple of reactions are going on. So you see why chemical thermodynamics is at the heart of everything around you. And that is why this topic is very important. So it involves a series of rules and laws that explain how it and work. Okay, so I didn't correct this on this slide. Okay, so this is supposed to be, it involves a series of rules and laws that explain how it and work. So rather than rather than you using how it and work is how it and work relates to each other. So how it and work relates to each other and explains which processes can happen spontaneously and which need some help. So thermodynamics tells you about reactions. Will this reaction occur on its own? Or will this reaction need some external force? Will it need some additional help? That's chemical thermodynamics. And that's one of the major difference between chemical thermodynamics and chemical kinetics. At some point in this course, we're also going to talk about chemical kinetics. So we're just going to have a brief comparison between thermodynamics and kinetics. Now, kinetics tells us our rate of a reaction depends on the pathway from reactant to product. You see, I love thermodynamics. I love kinetics. Everything I do in chemistry is centered around these two. So when you say thermodynamics and you say kinetics, I will just be smiling because this is what we are all about as physical chemists. Of course, there are some additional things, but at the heart of everything, we are looking at the thermodynamics and we are looking at the kinetics. So you hear some reactions at some point, they'll tell you this reaction is thermodynamically favored or thermodynamically stable, but kinetically, no. Or you hear this is kinetically controlled. Do you understand? Some reactants are kinetically controlled, while some are thermodynamically controlled. There are two different things. So kinetics tell us about the rate of the reaction, how fast a reaction proceeds, how it moves from reactant to product, while thermodynamics tells us whether a reaction is spontaneous based only on the properties of reactant and product. So thermodynamics is not thinking about the individual steps in the reaction. It's not bothered. Okay, so this is what we have here. The whole of this place, thermodynamics is not concerned with it. Whatever happens here, thermodynamics is not bothered with it. You have reactants and products. That's all thermodynamics is all about, the initial state and the final state. Meanwhile, kinetics is going to take into cognizance everything that is happening in between the reactant and the product. The combination of these two is what we discuss in mechanism of reaction. So when you want to do a mechanistic study of a reaction, you want to talk about the kinetics and you want to talk about the thermodynamics. All right, so why is thermodynamics very useful? Like I said, thermodynamics is at the heart of just think about anything, almost anything. Thermodynamics is at the heart of it. It gives you a qualitative explanation of materials, both qualitative and quantitative explanation of materials behavior. So when you see people working in the materials industry, they need to understand the thermodynamics behind their operations. And then the physical significance of thermodynamic functions is also something that is very, very relevant. And we're going to see that by the time we start talking about some of these thermodynamics functions, such as the enthalpy and the rest of it. All right, so some other applications that you can look at as in real life, some of the industries where you can use thermodynamics is in extraction and refinery, in corrosion industry. When you talk about corrosion, you're looking at oil firms. Remember, oil companies pass fuel via the pipeline. You want to know the rate of corrosion of these pipes. For you to understand the corrosion of these pipes, you need an understanding of thermodynamics. When you're looking at phase transformation / phase diagram calculation, you need your knowledge of thermodynamics. Materials processing, like I said earlier, you need your thermodynamics. Design of new materials, think about it. whatever material you want to design, you need to look at the thermodynamic aspect of the reaction. So thermodynamics is something you cannot avoid. The earlier you grasp it, the better. And for those of you who think, I'm not in the department of chemistry, why should I worry myself with this thermodynamics ish? Please, thermodynamics is everywhere. Thermodynamics is in biological system. Thermodynamics is in the industry. Thermodynamics is in the air you breathe in. So you can't avoid it. Just love it. That's my advice. You also have, can you see? So this is what I'm talking about. Even in your human body, thermodynamics is there. I talked about it, biological system. So when you're looking at the interaction of drugs in the body, for you to design drug for any ailments in the body system, you need to understand the binding affinity of these drugs with your protein or your enzymes. You need to understand the binding affinity. And for you to understand binding, you need thermodynamic functions to calculate this. In the aeroplane, that's you need thermodynamics and conditioning system. Just think about it. Anything you can think about, thermodynamics is at the heart of it. So please enjoy this roller coaster. It's going to be a whole lot of fun for CHM 121, CHM 222, wherever it is you are coming across thermodynamics. Just keep loving it because it has application everywhere. Now, to understand thermodynamics, it's helpful to first define some thermodynamic terms. And like I said, today's class is majorly about terms. We're just designing and defining terms, trying to understand these terms. By your next class, we'll then go into the full discussion, like an introduction of the full discussion of thermodynamics. Now, what is a system? When you say system in thermodynamics, a system is a series of components that are connected together. It means the parts of the world we are focusing on. So the world is very large. This is my cup of coffee. So I have a mug here and I drank LinkedIn this morning. Okay, I drank LinkedIn this morning. This mug right here is my system. So I added my tea bag, sugar, milk, and the rest of it. They are all part of my reaction. But this is my reaction vessel. And that is what we call is, oh, thank God I even have this cup on this table. I didn't plan this. It's just spontaneous. Okay, so it's so when I say it's spontaneous, what kind of reaction is that? We haven't got there. Anyway, so this is very spontaneous. So I have my cup of coffee here. So this mug right here is my system. I'm still going to refer to this mug today. So this is a system here. So this hand right here is not part of my reaction. This here is not part of my reaction because I'm not looking at here. This is another system on its own. But this particular mug is my system. So what I'm concerned about in my reaction is the content of this mug. Okay, so we can look at what moves in and out of a particular system. So I can look at what, and I'm going to talk about so many things that came into this mug and some of the things that happened within this mug, the things that came in and the things that went out of the mug. So we can look at what moves in and out of a particular system. For example, if we have a coffee in a thermos flask, that's what we call a water flask. That's what we call it regularly here. Water flasks. Everybody who has trained a baby, who has been with their mom or their aunts when they had babies, you all know water flask. So, for example, if we have coffee in a thermos flask, we can either call the coffee itself, the system, or the old thermos flask, including the walls of the container, a system. Now, in this case, I've chosen this as my system. And like I said, this mug is my system. And I'm considering this mug and everything within it as part of my system. So when we also talk about system, another thing we talk about is the kind of boundary. Sorry. I won't be able to see your charts now. Okay. When I ask for charts, then okay, let me just bring it up so I can see if you're asking questions. I can quickly pick it and time. Okay, this is better now. So we can have, From this diagram now, you have a system. You have a system, which is this here. Now, this thin lining is your boundary. In this case, this is my boundary. This surface area is my boundary. This cup, just right outside this cup, this mug is where my boundary starts from, either in or out. This is the boundary. This is what limits my system to where it is. And then surrounding is whatever, including myself, whatever you have outside of this boundary, my and everything out here is my surrounding of the system. So thermodynamic system and surrounding are separated by an envelope called boundary. So my boundary is this mug. It can be of two types. It can be adiabatic. This is the boundary which does not allow its transfer. This is the boundary which does not allow its transfer. In this case, okay, quickly type in the chat box. Would you say my mug is adiabatic or diathermic? Diathermic is a boundary which allow its transfer. Would you say my mug is adiabatic or diathermic? But somebody says what happened without any extra? Oh, okay, thank you. When I asked about fun, thank you very much. Diathermic. Okay, Evangelist, I can see yours. Diathermic. Okay, it's diathermic. Those of you that are writing thermic, yes, correct. Diathermic. Thank you very much. So this boundary allow its transfer. So my mug is a diathermic boundary. So we can either have adiabatic or diathermic. Adiabatic, it is not allowed. It does not allow its transfer. No, it is transfer, not any form of molecules is transfer. So thermodynamic system. In thermodynamics, a system is a part of the world in which we have a special interest. The surroundings are where we make our observations. The surroundings, which can be modeled, has a large water bath. So in this case, we have a universe here. This is our system right here, and this is our surrounding. In chemistry, when we want to carry out a reaction at constant temperature, this is what we do. You can see that this surrounding is in large excess, like is in excess of the system. So whatever change this system is going to be causing on this surrounding is going to be very inconsequential. So if this, for instance, is kept at a particular temperature, invariably, this system will be at that temperature. So if this is at a constant temperature, this will invariably be at that temperature. Anyway, so let's move on. The surroundings are where we make our observations. The surroundings, which can be modeled as a large water bath, so these are large water baths, remain at constant temperature regardless of how much energy flows into or out of them. They are so huge that they also have either constant volume or constant pressure, regardless of any changes that take place to the system. So regardless of what takes place here, this guy here is constant. Thus, even though the system might expand, the surroundings remain effectively the same size. You can see no matter how much, if this test tube or boiling tube or whatever we want to call it expands, it's the size of its expansion is still inconsequential to the size of this water bath here. So that's what we mean by the system might expand, the surroundings remain effectively the same size, because that expansion doesn't really change much in the surrounding. Now we need to distinguish three types of system. A system can either be open, like the case of my mug. An open system can exchange both energy and matter with its surroundings, and hence can undergo changes of composition. Now, in the case of my mug, can you give a diabatic system? Your thermos flask, your insulated thermos flask is an example of an adiabatic system because it doesn't allow the exchange of heat nor the exchange of matter. And my next question was going to be, I said that, I shouldn't have answered that question. Anyway, I said this is an open system. My mug is an open system. And the definition of an open system says an open system can exchange both energy and matter with its surroundings. So what is the matter this mug is exchanging with the surrounding? Quickly, what is the oh, thank you, David. David said vapor. Yes, when I pour us water in this mug, because it is an open system, the vapor was still coming out of the system. That vapor, remember, is matter. It's water in gaseous form, so it is matter. And also the heat was coming out. When I touched the mug was hot, and I could feel it on my hands. And I placed it on my cheek, I can feel the difference between, the temperature. So that is the heat, that's the energy. It can exchange both energy and matter with its surroundings. Now, a closed system is a system that can exchange energy but not matter with its surrounding. So assuming this cup was closed, assuming the cup was closed and this mug is not insulated, it means this mug can only exchange heat, because this vessel is going to get hot and I'm going to feel the heat on the outside. So it is exchanging only heat. It is a closed system. But when you have an isolated system, neither matter nor energy can be exchanged with its surrounding. So we have an example of an open system, a flask that is not stoppered and to which various substances can be added. A biological cell is an open system because nutrients and waste can pass through the cell wall. You and I are open system. We ingest, respire, perspire, and excrete. So we are open. An example of a closed system is a stoppered flask. Energy can be exchanged with the contents of the flask because the walls may be able to conduct it. An example of an isolated system is a sealed flask that is thermally, mechanically, and electrically insulated from its surroundings. So you have an example here. Here you can see your pot, your open pot, you have water in it, which is the matter. You have energy going out of this pot. When you touch the pot, you can see that the pot is hot. So both energy is going out, matter is going out. That's an open system. In this case, the pot has been covered. The pot has been covered and matter does not go in or out. Please, can somebody type an example of a closed system? Something that you use in cooking. Oh, why did I say that? An example, an example of a closed system in this form. A kettle, no. A kettle is not a closed system. A kettle, banjo, no. A pot, closed system. A closed pot of boiling rice, okay. That's okay. Flask, oven, oven. Oven, it's what you put in an oven. That oven itself is not oven itself is a closed pot. Okay, I like the idea of the pressure pot. Thank you, Bankole. That's what I was waiting for. A pressure cooker, a pressure pot. It's tightly covered. Tightly covered does not allow the exchange of heat, exchange of matter. But when you touch the body of the pot, you would see that it's very hot. Yes, very hot. So that does not allow the exchange of matter. Then an isolated system is your food flask. You have your flask. The surrounding within this flask is some kind of insulation to keep the temperature. So matter does not go in or out. Neither does energy. Neither does energy goes out of it because it has been insulated. Thank you very much. So another example, differences between individual types of chemical systems may be demonstrated using the example of making coffee. No, I'm not going to go to this. So just read it up. Now, phase, we need to talk about phase, homogeneous and heterogeneous system. When you talk about phases in thermodynamics, what are we saying? The term phase is used for that portion of the investigated system volume in which its properties are constant or continuously changing in space. So a system consisting of a single phase is called homogeneous. homogeneous system. If a system contains more phases, we call it a heterogeneous system. I'm sure heterogeneous, homogeneous is not strange to you. We talked about that in our mixture, heterogeneous and homogeneous mixture. So this is another example. Let's imagine a bottle of whiskey. How many phases does the system consist of? As much as I would have wanted us to discuss this, the time is not on our side. But we've used the example of our mug to explain this. So when you're talking of how many phases does a bottle of whiskey has, you can look at it as 2 or 3, depending on the system you want to observe. If you're looking at the whole bottle of whiskey with the content in the bottle of whiskey, then you're talking about 3 phases. The bottle itself is solid state, the liquid volume of the whiskey is liquid state, and then you know that there are some dissolved gas in the whiskey. If you're going to consider the dissolved gas in the whiskey, then we are looking at 3 phases: the air and the whiskey vapor, the whiskey liquid itself, and then its container. Now, thermodynamic process. In thermodynamic process, we can have a reversible and an irreversible process. If the properties of a system change in time, that is, if at least one thermodynamic quantity changes, we say that a certain thermodynamic process takes place in the system. The term process relates to a very broad range of most varied processes, from simple physical changes such as heating, various chemical reactions, up to complex multi-stage process. Individual kinds of processes may be classified according to several criteria. So some of the many basic one of the most basic process we can have in thermodynamic process is a reversible or an irreversible process. Then we also talk about processes at a constant quantity. So when you say that a reaction at constant temperature does this, does this, does this, does that, that's a process at a constant quantity. Sometimes we say constant temperature and pressure. Sometimes we only say constant pressure. So those are processes at a constant quantity. Then we also have cyclic processes. Reversible and irreversible processes. The course of any process depends on the conditions under which the given system changes. I've talked about this. So these processes are called irreversible. So you can read this up. You can read this up, reversible and irreversible processes. All right, thermodynamic. Okay, how many times do I? Okay, yeah. Now, processes at constant quantity. So this slide is talking about the reversible and the irreversible process. For instance, processes in real world are mostly such that system is out of equilibrium, at least at the beginning. So most of the process in real world are not reversible. So these processes are called irreversible. When you're looking at equilibrium processes, an equilibrium process is a reversible process. But most processes in real world are not at equilibrium, and therefore they are called irreversible processes. Now, when you talk about processes at constant quantity, I'm sure you are familiar with some of these processes. In most investigated processes, one or more thermodynamic quantities are maintained constant during the whole process. These processes are mostly termed using the prefix iso. So you hear isothermic or adiabatic and stuff like that. Those means processes at constant quantity. And a summary of some of this process has been listed on the table. You have isothermal, constant temperature; isobaric, constant pressure; isochoric, constant volume; adiabatic, constant heat; isentropic, isenthalpic, and polytropic. One of the most common ones that you should know, there's nothing hard in this table to know. But the moment somebody says isothermal, you know thermal has to come with it. And iso just tells you constant. So you know this is a process at constant temperature. Isobaric, you should know baric. Baric is pressure. Baric, pressure. Choric, volume. Adiabatic, heat. These four, very important because it is used often in questions. And if you don't know what this means, you don't even know where to start solutions from. So as a chemist, you can say this reaction is an isothermal process. So whoever you are talking with now, so those guys in art, or social sciences might probably not know, but it's an eyesore for somebody in science to not know what an isothermal process is. Okay, so example, in the initial state, a system of a constant volume has a temperature of 300 Kelvin and a pressure of 150 kilopascal. A certain process takes place in the system, and in the final state, the system's temperature is 320 Kelvin and its pressure is 150 kilopascal. Does the process take place under a constant thermodynamic quantity? So from the very first line, what would you call this system? Please, in 1 minute, type it in the chat box. From the very first line, what process would you call this process? Thank you, Banjo. Are you sure? Banjo, are you sure? Who else do we have? Banjo says isocoric. Banjo says isobaric. Banjo Ademosu. Okay. Itunu isocoric. Jemema isocoric. So Banjo has changed it. Isocoric. Thank you. Somebody says isobaric. Pressure is constant. From the first line. From the first line of this example. That's the question. We have not even got to the other part. From the first line, what does this tells you about this process? It's an isocoric, yeah, it's an isocoric reaction, yes, because it says in the initial state, a system of a constant volume. A system, David says, okay, that's fine. All right, so solution. The initial and the final temperatures of the system are different. Consequently, the process cannot be isothermal. Now, both the initial pressure and the final pressure are identical. In this case, it may be an isobaric process, but not necessarily. It's not necessarily an isobaric because some other changes might have happened at some point. The pressure might have changed and then it comes back to its initial pressure. So we need more information about this reaction to tell if it's an isobaric process or not. Now, the specification does not allow us to find out whether pressure changes in any way in the course of the process. However, the process is definitely an isocoric one because the system has a constant volume. Now, cyclic process. A cyclic process is such which the final state of the system is identical with its initial state. In a cyclic process, changes of thermodynamic quantities are zero. Note, heat and work are not thermodynamic properties, and therefore they are not zero during a cyclic process. So you can have an example, you can read up the example on the slides that will be shared with you after the class. So exothermic and endothermic process. This is a very common term that we talk about in thermodynamics. Remember, thermodynamics is the relationship between heat and work. So if you're talking heat, you're talking about heat. So when you say an exothermic process, in exothermic process, you're saying that heat is transferred from the system. Remember, your system is what you are studying. So heat is transferred from the system to the surrounding. In the case of the process that I carried out in this mug this morning, what process would you call it? Endothermic or exothermic? The process in my cup of tea this morning, is it an endothermic process or an exothermic? Thank you, Ademosu. Ademosu says exothermic because we have heat being transferred to the environment, to the surrounding, and this vessel was hot. So you can feel that my system is hot and is exchanging heat with the surrounding. Now, endothermic energy is the heat transferred from the surrounding to the system. So it is being transferred. So let's assume I have ice in this cup instead of hot tea. If it was ice, then what would be happening is an endothermic process because the temperature in this cup is lower than what you have in my surrounding, and therefore it is transferred from the surrounding into my system to melt the ice. So when you hear endothermic process, exothermic process. you should know the difference between these two processes. Another thing we talk about is intensive and extensive property. Intensive and extensive property. Any measurable quantity that is used to describe the condition or state of thermodynamic system is the property of that thermodynamics. Now we have two types of property, which is intensive or extensive. What is the difference? Thermodynamic property whose value is independent of size or mass or the extent of the system is known as intensive, is inherent, is an intensive property. So an example is temperature, pressure, density, surface tension, composition, viscosity, thermal conductivity, electrical potential. How do you tell whether this is intensive or extensive? Take temperature, for instance. If this water in the mug was 90 degrees Celsius, now remember that this is about 25 mil, 25 cm cube. If I took 1 cm cube of this water and I check the temperature, will it still be 99 or less? Quickly, just say more or less. If your answer is more, say more. If your answer is less, say less. So I have 25 mil of water here at 90 degrees Celsius. If I took 5 mil of the water at 90 degrees Celsius here and take the temperature reading, what would the temperature say? Thank you, David. David says same. Any other person? Lawal, same. So fine, same. The temperature is going to be the same. That's an intensive property. When you talk about extensive property, a thermodynamic property whose value depends on mass or extent of the system. Volume, that's very obvious. A volume is an extensive property because I just said something about volume here. So 25 mil is obviously different from 5 mil. You can see that it's obvious, it's different. Energy would also be different. Can somebody tell me why energy will be different? Quickly, why will energy be an extensive property? Let me give you an hint. Definition of energy. Mathematical expression of energy. Anyone? I'm waiting. We don't have much time. Anyone? Guys, come on. What's the the mass? Yeah, what's it about the mass? Michi says mass. What is it about the mass? We know that this depends on the mass or extent because energy is what? David is saying something. Because energy is work done. Yeah, so what is it about? What's the mathematical expression for energy? There's a relationship between mass and energy because the larger the mass, the higher the work done. Thank you. Because when you look at kinetic energy, for instance, the formula for your kinetic energy is what? Half mv squared, isn't it? Half mv squared. So you are going to expect that the mass, the energy is directly proportional to mass. So it is an extensive Thank you, Banjo. Thank you, Michi. All right, so let's move on. Whenever compounds or chemical reactions are discussed, one of the first things mentioned is the state of the specific molecule or compound. State refers to temperature, pressure, and the amount and type of substance present. Once the state has been established, state functions can be defined. And what is state function? State function is a property whose value does not depend on the path taken to reach that specific value. We're still going to talk about state function when we get into thermodynamics proper, when we start talking about the first law of thermodynamics and the subsequent laws. But you should know that a state function is a property whose value does not depend on the paths taken to reach that specific value. That's state functions. State functions are values that depend on the state of the substance and not on how the state was reached. So it is independent of the path. The other values that are not state values are called path functions. So when you say state function, the opposite of state function is path function. Path functions are dependent on how the state was reached. For example, density is a state function because a substance density is not affected by how the substance is obtained. Now let's look at kinetics and thermodynamics. Which of them is a state function? Quickly. We're looking at thermodynamics and kinetic. It's this hypothetical anyway from what we've said so far. Which of these two is a state function? Thank you, David. Remember, we say thermodynamics does not bother itself about how this part is reached. It's only concerned about the initial and the final state. So while kinetics, excuse me, while kinetics look at everything, all the individual steps that will lead you from reactant to product. Thank you, David. Thank you, Agomo. Thank you, Ajayi. Thank you, Okunlaya. I saw all your charts. Now, for example, okay, I said density is a state function because the substance density is not affected by how the substance is obtained. Consider a quantity of water. It does not matter whether that water is obtained from the tap, from a well, or from a bottle, because as long as all three are in the same state, they have the same density. They have the same density. So density. Now, finally, work. This is just an introduction. Just have like an example, a rough definition, a rough terminology in terms of thermodynamics, because we're still going to go into work proper, and that will be from the next class. Work. Work is the ability to move or change matter. You know, the class is becoming very exciting now, so that's why I'm all smiles, because we're beginning to get into the heart of the matter. So work is the ability to move or change matter. When work, this is important, when work is done on the system, when work is done on your system, we say it is positive. We say it is positive. Endothermic, exothermic, I think it should be out from there because endothermic and exothermic is talking about it. So please ignore this, ignore this. When work is done on the system, we say the value of work is positive. This convention is very important because when you have even your multiple choice questions, these are some of the conventions we'll be testing to see. If we say a particular system does work by expanding it, by expanding or whatever, you should be able to, because I'm going to give you the two values, both positive and negative. We want to be able to test your understanding of this convention. So in the terms of gas, when gas expands, we say that the system has done work. Because let's assume I have gas in this cup and I use a piston to cover this. If I press down the piston, remember I'm trying to increase the pressure of the gas in the cup. So if I press down the piston, I'm saying that I'm doing work on the system. So this system, the amount of work done on this system will be positive because the force is coming from external. But let's assume that the piston is somewhere in the cup and the gas in the cup is expanding. If it expands and pushes the piston up, then we'll say this system has done work, and that's going to make work negative. So when system does the work, we'll say that the work done by the system is negative. This shows that it's a system that is doing the work that we are calculating. Then in terms of heat too, when heat, when Q is positive, so I think this is where this endothermic and exothermic is supposed to come to, not the second and the third bullet. The second and the third bullet shouldn't have endothermic or exothermic. It's supposed to move to the third and the fourth bullet. Sorry for that. So when Q is positive, it means that it is added to the system. And that means that it is, okay, before I say that, is it endothermic or exothermic? 1, 2, 3, 4. The fourth bullet here, when it is positive, we are saying that it is added to this. Thank you, David. We say that it is added to the system. David says endo, Jemima endo. Thank you, everyone. Banjo, thank you. Lawal, thank you. I can see that. So we say that it is endothermic. But if Q is negative, that means that it is removed from the system or the system releases it to the surrounding. We say it is exothermic. On this note, we have come to the end of the class. On this note, we have come to the end of the class. In our next class, we'll be talking about work, heat, and its relationship, which is inherently the first law of thermodynamics.